Adam, what are you doing?
The team has been working a lot of late nights testing our new algorithm. Researchers, as you know, are fueled by pop and pizza. And well, the lab's starting to look like a scrapyard.
So, are you going to ban food in the lab?
No, you monster! I was thinking of programming a robot to drive around the lab and collect empty cans.
That sounds cool. How would it work?
Well, I think we need a vision system to recognize cans, obstacles, and people. The robot will also need to build a map and localize itself in the lab. Then we need to write some servoing routines to...
I'm going to have to stop you right there. I think there might be an easier way to do this. Let's solve it with reinforcement learning.
All right, RL. How would you do it, Martha?
Well, the reward could be the number of cans the robot collects. The agent could simply learn how to collect as many cans as possible through trial and error. In principle, it wouldn't even need a map of the lab. It could learn everything from scratch.
Right. That way, when somebody moves some furniture around, the robot could adapt automatically through learning. In fact, if one of the students starts drinking some new wild type of pop in pink cans, that would totally break a pre-learned perception system.
Yep. A reinforcement learning agent could simply try collecting the pink cans and find out itself they are worth collecting.
Okay, it sounds like we're going to need a good exploration method, and we'll definitely need function approximation if we want to learn from an onboard camera.
Yeah, and planning so that the agent can revisit parts of the lab it hasn't been to in a while to check for new cans.
But what about the reward function? What describes if the robot was successful?
Well, we could get one of the students to count the cans in the bin at the end of the day. If there were 6 cans in the bin, plus 6. No cans, 0 reward. So we'll probably need a TD-based algorithm to handle this delayed feedback. Before we get started, we better review the basics of reinforcement learning.
Well, the good news is everything we've just talked about will be covered in our new Coursera specialization on reinforcement learning.
That's amazing! Are the students really going to implement a can collecting robot?
No, but once they finish the specialization, they'll have all the conceptual tools they need to do so.
Either way, that's a lot of material. I think we're going to need a big team to cover all that stuff.
A team of RL experts. What a team!
Join us over the coming weeks right here in the RL AI Lab at the University of Alberta.
Welcome to the Reinforcement Learning Specialization from the University of Alberta on Coursera. Reinforcement learning is actually not that old. When I started back in the mid-2000s, it was a lot different than it is now. There were only a handful of labs around the world that focused on reinforcement learning. Almost nobody was using RL in industry, and the practical successes of RL were limited to a handful of applications. Reinforcement learning could fly a helicopter upside down better than any human could. RL methods could beat the world's best backgammon players and schedule elevators pretty well. But RL was not the best way to get robots to do useful things. And the idea that a Q-learning agent could play video games better than people was almost unimaginable. Yet we held out hope. Hope because we thought reinforcement learning was the best way to make progress towards AI. The promise of RL is almost intoxicating, that a learning agent can figure out how the world works by simply trying things and seeing what happens. After all, that's what we think people and animals do. So why not simulate that on a computer? If we could do it, then it would be useful in almost any application. And as a nice side effect, we might learn a good deal about how our own minds work too.
You might wonder, what's the difference between supervised learning, unsupervised learning, and reinforcement learning? The differences are quite simple. In supervised learning, we assume the learner has access to labeled examples, giving the correct answer. In RL, the reward gives the agent some idea of how good or bad its recent actions were. You can think of supervised learning as requiring a teacher that helps you by telling you the correct answer. A reward, on the other hand, is like having someone who can identify what good behavior looks like, but can't tell you exactly how to do it. Unsupervised learning sounds like it could be related, but really has a very different goal. Unsupervised learning is about extracting underlying structure in data. It's about the data representation. It can be used to construct representations that make a supervised or RL system better. In fact, as you'll see later in this course, techniques from both supervised learning and unsupervised learning can be used within RL to aid generalization.
In RL, we focus on the problem of learning while interacting with an ever-changing world. We don't expect our agents to simply compute a good behavior and then execute that behavior in an open loop fashion. We expect our agents to get things wrong, to refine their understanding as they go. The world is not a static place. We get injured, the weather changes, and we encounter new situations, and our goals change. An agent that immediately integrates its most recent experience should do well, especially compared with ones that attempt to perfectly memorize how the world works.
The idea of learning online is extremely powerful and is a defining feature of RL. The way we introduce concepts is dictated by this fact. For example, we introduce the ideas of bandits and exploration first and get to ideas from supervised learning later. This might feel backwards for you if you have a background in machine learning. But as you'll see, the hard part is learning online rather than just learning from data. Getting comfortable with the online setting requires a new perspective.
Today, the field of reinforcement learning feels like it's changing at a breakneck pace. There are almost weekly posts about new algorithmic developments and improvements in state-of-the-art performance in benchmark domains. Search companies, online retailers, and hardware manufacturers are exploring RL solutions for their day-to-day operations. They are convinced that online learning will make them more efficient, save them money, and keep humans out of dangerous situations. I would never have guessed that there would be companies dedicated to the study and application of reinforcement learning. It's really quite amazing. However, the more quickly things change, the more important it is to focus on the fundamentals. Some of the ideas in RL can be traced as far back as Pavlov and his drooling dogs. Take almost any modern RL system and take a closer look. It's built from ideas and algorithms that predate this specialization by a decade or two. For example, at its heart, DQN combines Q-learning, neural networks, and experience replay. Getting good performance out of these systems, however, required significant innovation. We would never downplay the importance of that work. In fact, we want you to come to understand these complex and large learning systems. To do so, you first need to understand the basics.
And that's where this course starts, with the fundamentals. In this specialization, we will cover most of the main ideas used in modern RL systems. And by the end, you will implement a neural network learning system to solve an infinite state control task. But we will start with small problems. We'll spend time discussing the fundamental challenges in reinforcement learning and our best ideas for solving them. The problem of sequential decision-making represents one of the greatest prizes of our generation. It seems appropriate to take our time and get the details right. We begin our study with a special case of the reinforcement learning problem called multi-armed bandits. The agent must decide which choice generates the best outcome or reward on average. This simpler instance of the full RL problem is perhaps the best setting to understand and solve challenges fundamental to RL. This module provides an introduction to estimating values, incremental learning, exploration, non-stationarity, and parameter tuning. We continue to develop and combine these ideas in different ways over the next 4 courses. Let's get started. Hi, I'm Martha. I'm an assistant professor at the University of Alberta.
Hi, I'm Adam. I'm a research professor at the University of Alberta and a senior researcher at DeepMind.
Adam is well known for his work on predictive knowledge for reinforcement learning. Several research groups around the world are building on these ideas. I personally think it is some of the most important work in recent years and will only become more influential. He's also an impressive empiricist, a real master of designing experiments to cut to the key issues. He's constantly trying to improve scientific understanding in the RL community.
Martha's algorithmic contributions to reinforcement learning are too many to list here. She has developed several new off-policy learning algorithms, new approaches to policy gradient, and dozens of impressive contributions to representation learning. She is truly one of the young, rising stars in reinforcement learning. She also happens to be my most frequent co-author and my partner in life.
So how did you get into computer science?
Well, I grew up on the East Coast. In high school, I was really interested in the sciences, physics, chemistry, biology, but I couldn't really find a right fit. And so I kind of randomly took a course on computer science and programming, actually, in GW Basic. And it was really just a career-defining moment for me because I just remember the first time, implementing an if statement or a for loop, and it was just amazing to me that I could get a computer to execute a sequence of instructions for me. And so from there, like, there was no hope. I was always going to do computer science in college.
Okay, and then from there, why did you start working on reinforcement learning?
So for graduate studies, I moved out to Alberta, and I came out here to do parallel distributed computing. That's what I kind of focused on in my undergrad. So I had all my courses loaded up with, systems courses, and I had one more elective to fill. And so I was looking around for a course to take, and I did a very reasonable strategy. I looked at the pictures of the professors, and I picked the friendliest looking professor I could find. And yeah, that turned out to be Rich Sutton, and it was Introduction to Reinforcement Learning. And that course was amazing. It was really inspiring. It was my first introduction to artificial intelligence or machine learning of any kind. And so I remember one of the early assignments in that course, we were implementing SARSA to do a grid world. And again, it was another career-defining moment for me, just watching this agent learn to solve this maze. And all it got was this reward signal, -1 per step. And somehow it figured out this amazingly efficient path out of the maze. And again, it just amazed me, and I was hooked, and I was going to keep doing that for the rest of my life. So Martha, how did you end up doing research in machine learning and artificial intelligence?
Well, I actually started my undergrad in math. I've always thought functions and dynamical systems are beautiful. And then I just took a CS course for fun, and it really was very fun. So I just continued in both math and CS. And those two topics go really well together for AI and machine learning, actually. So and then I did some research in AI in the summertime and just continued from there. And I really just stayed in the field because over time I realized it was more than just about functions and math. It's really a community where you get to collaborate a lot and you get to make a career where you help people. So my day, I get to mentor a lot and I get to work in a big team working on hard problems, and it's really just very amazing to get to work on such interesting questions in a team. So there's probably some people who are taking this RL course because they want to do graduate studies in RL. So what's one of the most important things you learned in your graduate studies?
Well, maybe surprisingly enough, I learned a lesson that's useful across probably all the sciences and in fact just any form of research. And that's to really love coming to understand the details of things, to focus and do small problems and understand them really, really well. And that's something that I think is really applicable across a wide range of things, and it's something that I pass on to my students in my classes, and I really focus on teaching my graduate students that, and it's something that I hope to share to the people taking this specialization.
So what do you like about your job?
Well, I love doing research, but sometimes that can kind of grind you down a little bit. Like, it's really long hours, the peer review process can be a little frustrating. And so in those times when you kind of step back and look at your research, it can seem kind of small and a little bit insignificant, and it's hard to see where that's going, how that's going to impact the world and make it a better place. And so in those times, you can always fall back and think about teaching and mentorship, right? Teaching is where you get to help people learn about things for the first time, to come to understand how your field works, and it's just so exciting. And you're also being part of the beginning of their careers, whether they end up in academia or industry or starting their own companies. It's just such an amazing experience to be part of that process. And throughout my week, the best day for me is always the days when my schedule is full of meetings with my students and I get to help them work on their problems and come to understand reinforcement learning better. So why do you think it's so important to work on reinforcement learning?
Well, I think the promise of RL is really big, but there are still a lot of open challenges. Machine learning has started being used much more widely, but RL has kind of only been used in a few areas. But at the same time, I think RL can have a really big impact. And I think within the next decade or so, we're going to see more control engineers actually using RL in their systems. We're really just going to see that it's a tool that can help in automated decision making, really within larger engineered systems. But I think for that to really happen, we need to make some advances in RL. We need to start thinking more about how we're going to have robust algorithms and how we're going to get people to be comfortable using these algorithms. So I think alongside adoption in industry, we're going to need to be thinking about how we can improve RL algorithms so that these two things can happen together. So how about you? Why do you think RL is good to work on?
Well, naturally, I think reinforced learning is just the exact right framework to study AI and to make progress towards solving AI. But RL is also really important to me because I'm very interested in developmental learning systems. So you can think about, humans, babies playing on the floor or young animals learning about the world. I want to learn about those systems and how they work. And if you think about those systems, they learn an enormous amount in such a tiny amount of time, right? They learn how to crawl, they learn how their bodies work, they learn how to interact with their environment, manipulate objects, communicate with other agents in the world, and there's just generally they're very competent learning systems, and they do that over like a couple weeks to a couple months, and it's just really astounding. And it feels like we have so much work to do to get close to those kind of systems. And so I really want to come to understand the algorithms and the representations that those systems might be using. And I think reinforcement learning is the right lens to look at those things and to come to understand those things. So applications always kind of drive interest and excitement in the field, and we've had a few of them in games and some industrial control problems. But what do you think is going to be the next big thing in reinforcement learning?
Well, at its heart, I think RL is just a general approach to automated decision making. It's a tool that's going to help us in a lot of our engineered systems. And so I think the place we're really going to see it take off is in industrial control. In industrial control, we have experts that are really looking for ways to improve how well their systems work. And so we're going to see it do things like reduce energy costs or save on other types of costs that we have in these industrial control systems. And in the hands of experts, we can really make these algorithms work well in the near future. So I really see it as a tool that's going to facilitate experts in their work rather than, say, doing something like replacing people or automating them away.
Reinforcement learning is a hot topic. It seems like every week I hear about a new algorithm or new application of reinforcement learning.
On the other hand, the fundamentals of RL are much the same. State-of-the-art learning systems are often constructed from a few well-known ideas, which are actually not that complicated. Take DQN, for example. This learning system combines Q-learning, epsilon greedy action selection, neural network function approximation, and a few other ideas to achieve superhuman scores in Atari games. In this one learning system, we see many of the most common building blocks of RL systems.
This course will closely follow Sutton and Bartow's new edition of Reinforcement Learning and Introduction. The first edition trained 2 generations of RL researchers, including Martha and myself.
The RL book and this specialization adhere to a simple principle: introduce each idea in the simplest setting it arises. In this spirit, we begin our study with multi-arm bandit problems. Here we get our first taste of the complexities of incremental learning, exploration, and exploitation.
After that, we move on to Markov decision processes to broaden the class of problems we can solve with reinforcement learning methods. Here we will learn about balancing short-term and long-term reward. We will introduce key ideas like policies and value functions used in almost all RL systems.
We conclude Course 1 with classic planning methods called dynamic programming. These methods have been used in large industrial control problems and can compute optimal policies given a complete model of the world.
In Course 2, we build on these ideas and design algorithms for learning without a model of the world. We study 3 classes of methods designed for learning from trial and error interaction. We start with Monte Carlo methods and then move on to temporal difference learning, including Q-learning. We conclude Course 2 with an investigation of methods for planning with learned models.
In Course 3, we leave the relative comfort of small finite MDPs and investigate RL with function approximation. Here we will see that the main concepts from Courses 1 and 2 transfer to problems with large or infinite state spaces. We will cover feature construction, neural network learning, policy gradient methods, and other particularities of the function approximation setting. You'll notice that the specialization starts off with basic material, but by the end of Course 3, you'll see how much we build on simple concepts introduced early on. You'll finish Course 3 and wonder how it is that you learned so much when it all seemed pretty simple at the time.
The final course in the specialization brings everything together in a capstone project. Throughout this specialization, as in Rich and Andy's book, we stress a rigorous and scientific approach to RL. We conduct numerous experiments designed to carefully compare algorithms. It takes careful planning and a lot of hard work to produce a meaningful empirical result. In the capstone, we will walk you through each step of this process so that you can conduct your own scientific experiment. We'll explore all the stages from problem specification all the way to publication quality plots. This is not just academic. In real problems, it's important to verify and understand your system. After that, you should be ready to test your own new ideas or tackle a new exciting application of RL in your job.
We hope you enjoy the show half as much as we enjoyed making it for you. Imagine that you're going out to eat with your friends tonight. When you get to the restaurant, you will have to decide what to order. You've been there a few times before and you always order the same thing, so you know that you will be quite happy if you order it again. Many of the other items, though, look really tasty. How do you decide when to order the same good meal again or try something new? By the end of this video, you will be able to define the exploration-exploitation trade-off, and you will be able to define epsilon greedy, which is a simple method to balance exploration and exploitation. Before discussing the trade-off, let's first talk about when we would want to explore and when we would want to exploit. Exploration allows the agent to improve its knowledge about each action, hopefully leading to long-term benefit. By improving the accuracy of the estimated action values, the agent can make more informed decisions in the future. Here's an example of exploratory behavior. Let's say each of these plates represents a meal at your favorite restaurant, and you're trying to choose which meal to order. Q of A is the estimated value for picking that meal. N of A is the number of times you have picked that meal. Q star of A is the value of each meal. Each time you visit this restaurant, you follow a strict regimen and choose each meal in a round-robin fashion. Perhaps a meal is sometimes cooked particularly well, so you are highly rewarded for ordering it. After some time, you'll find the best meal to order. Exploitation, on the other hand, exploits the agent's current estimated values. It chooses the greedy action to try to get the most reward. But by being greedy with respect to estimated values, may not actually get the most reward. Let's look at how pure greedy action selection could lead to suboptimal behavior. Imagine the agent selects the first meal. The agent received a positive reward, making the value for that meal higher. The estimated values for the other actions are 0. So the greedy action is always the same, to pick the first meal. This means the agent never saw any samples for the other meals. The estimated values for the other two actions remain far from the true values, which means the agent never discovered the best action. This naturally introduces the exploration-exploitation dilemma. How do we choose when to explore and when to exploit? When we explore, we get more accurate estimates of our values. When we exploit, we might get more reward. We cannot, however, choose to do both simultaneously. One very simple method for choosing between exploration and exploitation is to choose randomly. We could choose to exploit most of the time with a small chance of exploring. For instance, we could roll a dice. If it lands on 1, then we'll explore. Otherwise, we'll choose the greedy action. We call this method epsilon greedy, where epsilon refers to the probability of choosing to explore. In this case, epsilon would be equal to 1 over 6. We can write epsilon greedy in the following way. The action that we select on time step t is the greedy action with probability 1 minus epsilon, or is a random action with probability epsilon. We can demonstrate the effectiveness of epsilon greedy action selection on the 10-arm testbed from the textbook. The 10-arm bandit problem has 10 actions, here shown along the x-axis. On the y-axis, we'll show the distribution of rewards. Each reward is sampled from a normal distribution with some mean Q star of A and variance 1. Each Q star of A is drawn from a normal distribution with mean 0 and variance 1. Each time we run the 10-arm testbed, Q star will be redrawn from a normal distribution. Notice how much randomness is involved in this experiment. Q star is randomly sampled from a normal distribution, the rewards are randomly sampled based on Q star, and the actions are randomly taken on exploration steps. To fairly compare different algorithmic choices, we will need to perform many independent runs. Let's take a look at a single run of an epsilon greedy agent in the 10-arm testbed. For this agent, we set epsilon equal to 0.1. The time step is on the x-axis. The y-axis is the reward received on that time step. Notice how noisy this curve is, with several sharp peaks. We sort of see a slight upward trend in the center of these peaks, but with this amount of noise, it is hard to make any conclusions. If we run another agent with a different random seed, we get another noisy curve. And a third run. For every time step, we can take the average of each of these three rewards we've seen on that time step. This will produce a single line that represents the average reward received for each of these three runs. For example, here's what happens when we take 20 such runs and average the reward. Notice that the spikes in the curve are much less pronounced. If we take 100 runs and average them together, we see a much more clear shape to the curve. There's a noticeable increase in reward in the first 200 steps. And doing this with 2,000 runs, we get a clear picture of the performance of this method. What this result says is that this way of behaving obtains this much reward in expectation across possible stochastic outcomes. Throughout this specialization, we use the average performance over many independent runs to make scientific comparisons. Without using summary statistics like the average, it would be difficult to make fair comparisons between algorithms. In this example, the random seed is the only difference between runs of this epsilon greedy agent, and yet the performance looks quite different. Okay, let's go back to the experiment on the 10-arm testbed. We are going to compare epsilon greedy agents with different epsilons. Let's start by investigating the average reward obtained by each algorithm. The time step is shown on the x-axis. The average reward over 2,000 runs is on the y-axis. Here's the performance with epsilon equal to 0. When epsilon is 0, the agent performs no exploration steps, only greedy steps. Here's the performance of epsilon equals 0.01. Notice that the average reward keeps improving over time. This method explores 1% of the time and eventually converges to taking the optimal action 99.1% of the time. The agent with epsilon equal to 0.1 obtains more reward earlier on average than the other methods, but it plateaus after 300 steps. In this lecture, we discussed the trade-off between exploration and exploitation. We also discussed epsilon greedy, which is a simple method for balancing exploration and exploitation. Later, we will discuss more sophisticated methods for choosing between exploration and exploitation. What if our doctor performing medical trials was initially very optimistic about the outcome of each treatment? This principle of being optimistic in the face of uncertainty is a common strategy for balancing exploration and exploitation. Today, we'll discuss how to implement this idea using optimistic initial values. By the end of this video, you will understand how optimistic initial values encourage early exploration and be able to describe some of the limitations of optimistic initial values as an exploration mechanism. Let's consider how optimism affects action selection, using our doctor again as an example. Perhaps the doctor starts with the assumption that each treatment is 100% effective until shown otherwise. Our doctor would begin prescribing treatments at random until one of the treatments fails to cure a patient. The doctor might then choose from the other two treatments at random. Again, the doctor would continue until one of these treatments fails to work. The doctor would continue this way, always assuming that treatments are maximally effective until shown that the estimated values need to be corrected. Let's see how this works with explicit values. Previously, the initial estimated values were assumed to be 0, which is not necessarily optimistic. Now, our doctor optimistically assumes that each treatment is highly effective before running the trial. To make sure we are definitely overestimating, let's make the initial value for each action 2. Let's assume the doctor always chooses the greedy action. Recall the incremental update rule for the action values shown to the left. Let's take the alpha equal to 0.5 for this demonstration. The first patient comes in. Because the values are all equal right now, the doctor chooses a treatment randomly. The doctor prescribes treatment P, and the patient reports feeling better. Notice that the estimated value for treatment P decreased from 2 to 1.5, even though the treatment was a success. This is because the reward was 1, which is less than our initial optimistic estimate of the value. The next patient arrives. The doctor chooses amongst the treatments with the highest estimated value, treatment Y or treatment B. The doctor randomly chooses to prescribe treatment Y. The patient reports that they do not feel better, giving a reward of 0. And the doctor lowers their estimated value for treatment Y. The estimated value decreased to 1, lower than the current estimated value for treatment P. A third patient comes into the clinic. Treatment B has the highest estimated value, and so the doctor prescribes treatment B. The patient reports feeling better, so the estimated value only decreases to 1.5. Patients keep coming in, and the doctor continually provides treatments and refines the value estimates. From this example, we can see that using optimistic initial values encourages exploration early in learning. The doctor tried all 3 of the treatments in the first 3 time steps and continued to try all treatments afterwards. Let's look at another example, this time the 10-armed bandit problem from the textbook. The values for each action are sampled from a normal distribution. For this problem, an initial estimated value of 5 is likely to be optimistic. In this plot, all of the values are less than 3. Whenever the agent selects an action, the first time that action is selected, the observed reward will likely be smaller than the optimistic initial estimate. The estimated value for this action will decrease, and other actions will begin to look more appealing in comparison. Let's run an experiment to see how an agent behaves with optimistic initial values. As a baseline, we can run an epsilon greedy agent with epsilon equals 0.1 and initial value estimates set to 0, which are not optimistic. We also run a greedy agent with optimistic initial values. We plot the percentage of time that the agent chooses the optimal action, averaged over runs. In early learning, the optimistic agent performs worse because it explores more. Its exploration decreases with time because the optimism in its estimates washes out with more samples. Using optimistic initial values is not necessarily the optimal solution for balancing exploration and exploitation. One limitation is that optimistic initial values only drive exploration early in learning. This means the agent will not continue exploring after some time. This leads to issues in non-stationary problems. For example, one of the action values may change after some number of time steps. An optimistic agent may have already settled on a particular action and will not notice that a different action is better now. Another potential limitation is that we may not always know how to set the optimistic initial values, because in practice, we may not know the maximal reward. Regardless of some of these limitations, optimistic initial values has proven to be a very useful heuristic. We will continue using this approach, often in combination with other exploration approaches, throughout the rest of this course. In this video, we discussed the effects of our initial value function estimates. We described how optimistic initial values encourage early exploration, and we demonstrated this through a couple of examples. We finally briefly described some of the limitations of optimistic initial values. See you next time when we will talk about another strategy to balance exploration and exploitation.
This week, you were introduced to the K-arm bandit problem and several fundamental concepts in reinforcement learning. We started by describing the problem setting. We have an agent taking actions and receiving rewards based on the action selected. We define the value of each action as the expected reward received when taking that action. The value function Q star is unknown to the agent. We then introduce the sample average method for estimating Q star. It uses the sum of rewards received when action A is taken, divided by the number of times A has been taken. We derived an incremental update rule by finding a recursive definition of the sample average. By doing so, we need only store the number of times each action has been taken, and the previous estimate. We then showed that we can make the step size more generic, and in fact, by using a constant step size, we could more effectively solve the bandit problems that change over time. Next, we ran into the issue of exploration versus exploitation. We defined exploration as the chance for the agent to improve its knowledge. some actions may be better than we realize. We have to try the actions we may not think are the best to improve our estimates. We define exploitation as the agent taking the action it currently thinks is best in the hopes that it will generate the most reward. The agent cannot explore and exploit simultaneously. So how do we choose when to explore and when to exploit? To answer this question, we introduced epsilon greedy action selection. Epsilon greedy explores epsilon percentage of the time and exploits 1 minus epsilon percentage of the time. When epsilon greedy exploits, it chooses the action which maximizes the current value estimate. When epsilon greedy explores, it chooses an action uniform randomly. We also investigated the effects of optimistic initial values. If the initial values are larger than Q star, the agent will systematically explore the actions. The optimism fades with time and the agent eventually stops exploring. Finally, we discussed upper confidence bound action selection. UCB mixes exploitation and exploration through the use of confidence intervals. UCB uses the strategy of optimism in the face of uncertainty. And that's it for bandits. This week, we introduced some of the most fundamental concepts in reinforcement learning. We can largely view the bandit problem as a subset of the larger reinforcement learning problem. Concepts like maximizing reward and choosing actions when faced with uncertainty are key to reinforcement learning. We're excited to begin introducing the full reinforcement learning problem next week. Be sure to read the textbook for the next week's lectures.
The KR and bandit problem we looked at previously introduces many interesting questions. However, it doesn't include many aspects of real-world problems. The agent is presented with the same situation at each time, and the same action is always optimal. In many problems, different situations call for different responses. The actions we choose now affect the amount of reward we can get into the future. The Markov decision process formalism captures these two aspects of real-world problems. By the end of this video, you'll be able to understand Markov decision processes, or MDPs, and describe how the dynamics of an MDP are defined. Let's start with a simple example to highlight how bandits and MDPs differ. Imagine a rabbit is wandering around in a field, looking for food, and finds itself in a situation where there is a carrot to its right and broccoli on its left. Our rabbit prefers carrots, so eating the carrot generates a reward of plus 10. Eating the broccoli, on the other hand, generates a reward of only plus 3. But what if later the rabbit finds itself in another situation where there is broccoli on the right and carrot on the left? Here the rabbit would clearly prefer to go left instead of right. The KR and bandit problem does not account for the fact that different situations call for different actions. It's also limited in another way. Let's say we do account for different actions in different situations. Here it looks like the rabbit would like to go right to get the carrot. However, going right will also impact the next situation the rabbit sees. Let's say just to the right of the carrot, there is a tiger. If the rabbit moves right, it gets to eat the carrot. But afterwards, it may not be fast enough to escape the tiger. If we account for the long-term impact of our actions, the rabbit should go left and settle for broccoli to give itself a better chance to escape. A bandit rabbit would only be concerned about immediate reward, and so would go for the carrot. But a better decision can be made by considering the long-term impact of our decisions. Now let's look at how the situation changes as the rabbit takes actions. We will call these situations states. In each state, the rabbit selects an action. For instance, the rabbit can choose to move right. Based on this action, the world changes into a new state and produces a reward. In this case, the rabbit eats the carrot and receives a reward of plus 10. However, the rabbit is now next to the tiger. Let's say the rabbit chooses the left action. The world changes into a new state where the tiger eats the rabbit and the rabbit receives a reward of minus 100. From the original state, the rabbit could alternatively choose to move left. Then the world transitions into a new state, and the rabbit receives a reward of +3. The diagram now shows two potential sequences of states. The sequence that happens depends on the actions that the rabbit takes. We can formalize this interaction with a general framework. In this framework, the agent and environment interact at discrete time steps. At each time, the agent receives a state ST from the environment from a set of possible states, script S. The configuration shown on the slide is an example of a state. Based on this state, the agent selects an action AT from a set of possible actions. Script A of ST is the set of valid actions in state ST. Moving right is an example of an action. One time step later, based in part on the agent's action, the agent finds itself in a new state ST+1. For example, this state where the rabbit is next to the tiger. The environment also provides a scalar reward, RT+1, drawn from a set of possible rewards, script R. In this case, the reward is +10 for eating the carrot. This diagram summarizes the agent-environment interaction in the MDP framework. The agent-environment interaction generates a trajectory of experience consisting of states, actions, and rewards. Actions influence immediate rewards as well as future states, and through those, future rewards. So how can we represent the dynamics of this interaction? As in bandits, the outcomes are stochastic, and so we use the language of probabilities. When the agent takes an action in a state, there are many possible next states and rewards. The transition dynamics function P formalizes this notion. Given a state S and action A, P tells us the joint probability of next state S' and reward R. In this course, we will typically assume that the set of states, actions, and rewards are finite. But don't worry, you will learn about algorithms that can handle infinite sets and uncountable sets. Since P is a probability distribution, it must be non-negative, and its sum over all possible next states and rewards must equal 1. Note that future state and reward only depends on the current state and action. This is called the Markov property. It means that the present state is sufficient, and remembering earlier states would not improve predictions about the future. That's it for this video. In summary, MDPs provide a general framework for sequential decision-making, and the dynamics of an MDP are defined by a probability distribution. In the next video, we will discuss several decision-making tasks and formalize each as an MDP.
In this video, we will explore the flexibility of the MDP formalism with a few examples. By the end of this video, you will gain experience formalizing decision-making problems as MDPs and appreciate the flexibility of the MDP formalism. Consider a recycling robot which collects empty soda cans in an office environment. It can detect soda cans, pick them up using its gripper, and drop them off in a recycling bin. The robot runs on a rechargeable battery. Its objective is to collect as many cans as possible. Let's formulate this problem as an MDP. We will start with the states, actions, and rewards. Let's assume that the sensors can only distinguish two charge levels, low and high. These charge levels represent the robot's state. In each state, the robot has three choices. It can search for cans for a fixed amount of time, it can remain stationary and wait for someone to bring it a can, or it can go to the charging station to recharge its battery. We only allow recharging from the low state because recharging is pointless when the energy level is high. Now let's consider the transition dynamics. First, let's draw the states using open circles. Searching for cans when the energy level is high might reduce the energy level to low. That is, the search action in the state high might not change the state. Let's say with probability alpha. Or the energy level might drop to low, with probability 1 minus alpha. In both cases, the robot's search yields a reward of R search. For instance, R search could be plus 10, indicating that the robot found 10 cans. The robot can also wait. Waiting for cans does not drain the battery, so the state does not change. In both cases, the wait action yields a reward of R wait. For example, R wait could be plus 1. Searching when the energy level is low might deplete the battery. Then the robot would need to be rescued. Let's write this probability as 1 minus beta. If the robot is rescued, then its battery is restored. However, needing rescue yields a negative reward of R rescued. For example, R rescued could be minus 20 because we are annoyed with the robot. Alternatively, the battery might not run out. This occurs with probability beta, and the robot receives a reward of R search. Taking the recharge action restores the battery to the level high and receives a reward of 0. And that's it. We have completely specified the MDP for the recycling robot problem. We have discussed one example where an MDP is used to precisely specify a problem. But you might wonder, how general is this framework? The MDP formalism can be used in many different applications in many different ways. States can be low-level sensory readings, for example, in the pixel values of the video frame. They can also be high-level, such as object descriptions. Similarly, actions can be low-level, such as the wheel speed of this robot. Actions can also be high-level, such as go to the charging station. Time steps can be very small or very large. For example, they can be 1 millisecond or 1 month. Let's look at one more application. Suppose we want to use reinforcement learning to control a robot arm in a pick-and-place task. The goal of the robot is to pick up objects and place them in a particular location. There are many ways we could formalize this task. Here's one possibility. The state could be the readings of the joint angles and velocities. The actions could be the voltages applied to each motor. The reward could be plus 100 for successfully placing each object. But we also want the robot to use as little energy as possible. So let's include a small negative reward corresponding to the energy used. That was not so hard. To recap, the MDP framework can be used to formalize a wide variety of sequential decision-making problems. In reinforcement learning, the agent's objective is to maximize future reward. Today, we will formalize this notion. By the end of this video, you will be able to describe how rewards relate to the goal of an agent and identify episodic tasks. Let's define the agent's goal. Perhaps we can just maximize the immediate reward, as we did in Bandits. Unfortunately, this won't work in an MDP. An action on this time step might yield large reward, but cause the agent to transition into a state that yields low reward. So what looked good in the short term might not be the best in the long term. Consider a robot learning to walk. The reward could be proportional to the forward motion. Lurching forward would clearly maximize immediate reward. However, this action caused the robot to fall over. If the robot maximized total forward motion instead, it would walk quickly but carefully. Now let's formally define what we mean by maximizing total future reward. The return at time step t is simply the sum of rewards obtained after time step t. We denote the return with the letter g. The return is a random variable because the dynamics of the MDP can be stochastic. To better understand this, imagine our can collecting robot starts here. From this state, the robot always takes the same sequence of actions. Sometimes it might get a large return, and sometimes it might get a small return. This is due to the randomness in both the individual rewards and the state transitions. In general, many different trajectories from the same state are possible. This is why we maximize the expected return. For this to be well defined, the sum of rewards must be finite. Specifically, let's say there is a final time step called capital T, where the agent-environment interaction ends. What happens when the interaction ends? In the simplest case, the interaction naturally breaks into chunks called episodes. Each episode begins independently of how the previous one ended. At termination, the agent is reset to a start state. Every episode has a final state, which we call the terminal state. We call these tasks episodic tasks. To understand episodic tasks better, let's look at a concrete example. Consider the game of chess. A game of chess always ends with a checkmate, draw, or resignation. What would an episode look like when playing chess? As you might have guessed, a single game of chess would constitute an episode. Each game starts from the same start state with all the pieces reset. Let's summarize what we learned. We formulated the goal of an agent in terms of maximizing the expected return. We then discussed episodic tasks, where the agent-environment interaction breaks up into episodes.
Hi, I'm Michael Littman. I'm a computer science professor at Brown University, and I was asked to speak about the reward hypothesis. Now, the basic idea of the reward hypothesis is illustrated in this famous saying: give a man a fish and he'll eat for a day. Teach a man to fish and he'll eat for a lifetime. Give a man a taste for fish and he'll figure out how to fish even if the details change. Okay, maybe it's not a famous saying, but someone who isn't me retweeted it, so that's something. Anyway, there are three ways to think about creating intelligent behavior. The first, give a man a fish, is good old-fashioned AI. If we want a machine to be smart, we program it with the behavior we want it to have. But as new problems arise, the machine won't be able to adapt to new circumstances. It requires us to always be there providing new programs. The second, teach a man to fish, is supervised learning. If we want a machine to be smart, we provide training examples and the machine writes its own program to match those examples. It learns. So as long as we have a way to provide training examples, our machine will be able to write its own programs. And that's progress. But situations change. I mean, most of us don't have the opportunity to eat fish or to fish for our food every day. The third, give a man a taste for fish, that's reinforcement learning. It's the idea that we don't have to specify the mechanism for achieving a goal. We can just encode the goal, and the machine can design its own strategy for achieving it. I mean, these days, you don't have to catch a salmon to eat a salmon. There's supermarkets, there's seafood chain restaurants, and if all else fails, gas station sushi. So that's the high-level idea. But what about the hypothesis itself? Now, I'm pretty sure I got it from Rich Sutton. But I've heard that Rich Sutton attributes it to me. So if I'm going to tell you about it, I thought it would be a good idea to get a handle on the history of the term. Google Trends is an awesome service that provides information about how often a term is used historically. So when I asked it about the reward hypothesis, it said no dice. Searching for reward hypothesis reinforcement learning has 3,580 results, so that's something. On the first few pages of results, I found a few examples. A blog post by Mohammed Ashraf says, all goals can be described by the maximization of expected cumulative rewards. David Silver used the same phrase in his intro reinforcement learning course, but he spelled maximization with an S because he's British. Rich Sutton has a blog post called The Reward Hypothesis, and there he states it a little bit differently. He says what we mean by goals and purposes can be well thought of as maximization of the expected value of the cumulative sum of a received scalar signal, reward. This version emphasizes that it goes beyond goals and the fact that reward is a scalar, but overall the spirit is very much the same as the other versions I found. Okay, what about my version? So I searched my archive and I got no hits at all. Then I saw in that same essay that Rich said that I call it the reinforcement learning hypothesis. So that explains why I wasn't finding it. With the right term in hand, I was able to dig up this slide from a talk that I gave in the early 2000s. And it says, intelligent behavior arises from the actions of an individual seeking to maximize its received reward signals in a complex and changing world. Again, it's pretty similar to the others. I neglected to say cumulative and scalar, but I did contrast the simplicity of the idea of reward with the complexity of the real world. I also pointed out the implications of this idea. So if you buy into this hypothesis, it suggests that there's two main branches of research that need to be addressed. The first is to figure out what rewards agents should optimize, and the second is to design algorithms to maximize it. People have given a lot of attention to the first bullet. I'm going to focus on the second. How can we define rewards? Well, why is that even hard? Well, sometimes it's not. A reinforcement learning agent on the stock market can probably just be given monetary rewards to optimize. Buying actions cost dollars, selling actions generate dollars. The trade-offs are easy. There's a common currency, literally. This picture shows a reinforcement learning-based solar panel some of my students built. Moving the motors to reposition itself costs energy, and the sun shining on the panel brings in energy. So again, there's a common currency. But if we're designing a reinforcement learning agent to control a thermostat, what's the reward? Turning on the heat or air conditioning costs energy, but not turning on the heat or air conditioning causes discomfort in the occupants. So there's no common currency. I suppose we could translate both into dollars, but it's not very natural. How much are you willing to pay to move the temperature a little closer to your comfort zone? We typically define some units of cost for discomfort, but setting a precise value can be tricky. We can express the idea of a goal using rewards. One way is to define a state where the goal is achieved as having +1 reward and all others is 0 reward. That's sometimes called the goal reward encoding. Another is to penalize the agent with a -1 each step in which the goal has not been achieved. Once the goal is achieved, there's no more cost. That's the action penalty representation. In both cases, optimal behavior is achieved by reaching the goal, so that's good. But they result in subtle differences in terms of what the agent should do along the way. The first doesn't really encourage the agent to get to the goal with any sense of urgency. And the second runs into serious problems if there's some small probability of getting stuck and never reaching the goal. And both schemes can lead to big problems for goals with really long horizons. Imagine we want to encourage an agent to win a Nobel Prize. Come to think of it, that would discourage computer science research since there's no Nobel in CS. But my point is that we'd give the agent a reward for being honored in Sweden and 0 otherwise. That's really, really rough. Some intermediate rewards like +0.0001 for doing well on a science test or +001 for getting tenure could make a big difference for helping to point the agent in the right direction. So even if we accept the reward hypothesis, there's still work to do to define the right rewards. The FISH slogan provides 3 different places behavior could come from. We can use the same approach to talking about rewards can come from. Computer scientists love recursion. Programming is the most common way of defining rewards for a learning agent. A person sits down and does the work of translating the goals of behavior into reward values. And that can be done once and for all by writing a program that takes in states and outputs rewards. Some recent research looks at special languages for specifying tasks, like temporal logic. These languages might be useful as intermediate formats that are somewhat easy for people to write, but also somewhat easy for machines to interpret. Rewards can also be delivered on the fly by a person. Recent research focuses on how reinforcement learning algorithms need to change when the source of rewards is a person. People act differently than reward functions. They tend to change the reward they give in response to how the agent is learning, for example. Standard reinforcement learning algorithms don't respond well to this kind of non-stationary reward. We can also specify rewards by example. That can mean an agent learning to copy the rewards that a person gives. But a very interesting version of this approach is inverse reinforcement learning. In inverse reinforcement learning, a trainer demonstrates an example of the desired behavior, and the learner figures out what rewards the trainer must have been maximizing that makes this behavior optimal. So whereas reinforcement learning goes from rewards to behavior, inverse reinforcement learning is going from behavior to rewards. Once identified, these rewards can be maximized in other settings, resulting in powerful generalization between environments. Rewards can also be derived indirectly through an optimization process. If there's some high-level behavior we can create a score for, an optimization approach can search for rewards that encourage that behavior. So returning to the Nobel Prize example from earlier, imagine creating multiple agents pursuing this goal instead of a single one. That would allow us to evaluate not just the result of the behavior, was the prize won, but the rewards being used as an incentive for this behavior. And arguably, this is how living agents get their reward functions. Reinforcement learning agents survive if they have good reward functions and a good algorithm for maximizing them. Those agents pass their reward functions along to their offspring. More generally, this is an example of meta-reinforcement learning, learning at the evolutionary level that creates better ways of learning at the individual level. Personally, I think the reward hypothesis is very powerful and very useful for designing state-of-the-art agents. It's a great working hypothesis that has helped lead us to some excellent results. But I'd caution you not to take it too literally. We should be open to rejecting the hypothesis when it has outlived its usefulness. For one thing, there are examples of behavior that seem to be doing something other than maximizing reward. For example, it's not immediately apparent how to capture risk-averse behavior in this framework. Risk-averse behavior involves choosing actions that might not be best on average, but, for example, minimize the chance of a worst-case outcome. Oh, on the other hand, maybe you can capture this kind of behavior by intervening on the reward stream to magnify negative outcomes. That will shift the behavior in precisely the right way. What about when the desired behavior isn't to do the best thing all the time, but to do a bunch of things in some balance? Like imagine a pure reward maximizing music recommendation system. It should figure out your favorite song and then play it for you all the time. And that's not what we want. Although, maybe there are ways to expand the state space so the reward for playing a song is scaled back if that song has been played recently. It's kind of like the idea that an animal gets a lot of value from drinking, but only if it's thirsty. If it just had a drink, the reward for drinking again right away is low. So maybe rewards can handle these cases. Well, another observation that I think is worth considering is whether pursuing existing rewards is a good match for high-level human behavior. There are people who single-mindedly pursue their explicit goals, but it's not clear that we judge such people as being good to have around. As moral philosophers might point out, the goals we should be pursuing aren't immediately evident to us. As we age, we learn more about what it means to make good decisions, and generations of scholars have been working out what it means to be a good, ethical person. Part of this is better understanding the impacts of our actions on the environment and the impacts on each other, and that's just reinforcement learning. But part of it is articulating a deeper sense of purpose. Are we just identifying details of the reward functions that are already buried in our minds, or are we actually creating better goals for ourselves? I don't know, but in the meantime, we should entertain the possibility that maximizing rewards might just be an excellent approximation of what motivates intelligent agents.
In the previous video, we discussed episodic problems. In many problems, however, the agent-environment interaction continues without end. Today, we will see how such problems can be formulated as continuing tasks. In this video, you will learn to differentiate between episodic and continuing tasks, formulate returns for continuing tasks using discounting, and describe how returns of successive time steps are related to each other. Let's look at the differences between episodic and continuing tasks. As we discussed earlier, episodic tasks break up into episodes. Every episode in an episodic task must end in a terminal state. The next episode begins independently of how the last episode ended. The return at time step t is the sum of rewards until termination. In contrast, continuing tasks cannot be broken up into independent episodes. The interaction goes on continually. There are no terminal states. To make this more concrete, consider a smart thermostat, which regulates the temperature of a building. This can be formulated as a continuing task, since the thermostat never stops interacting with the environment. The state could be the current temperature, along with details of the situation, like the time of day and the number of people in the building. There are just two actions, turn on the heater or turn it off. The reward would be -1 every time someone has to manually adjust the temperature, and 0 otherwise. To avoid negative reward, the thermostat would learn to anticipate the user's preferences.
So how can we formulate the return for continuing tasks? We can try to sum up all the future rewards as we did for episodic tasks. But now we're summing over an infinite sequence. This return might not be finite. So how can we modify this sum so that it's always finite? One solution is to discount future rewards by a factor gamma called the discount rate. Gamma is at least 0 but less than 1. The return formulation can then be modified to include discounting. The effect of discounting on the return is simple. Immediate rewards contribute more to the sum. Rewards far into the future contribute less because they are multiplied by gamma raised to successively larger powers of k. Intuitively, this choice makes sense. $1 today is worth more to you than $1 in a year. We can concisely write this sum as this expression, which is guaranteed to be finite. Let's see why. Assume Rmax is the maximum reward our agent can receive at any time step. We can now upper bound the return gt by replacing every reward with Rmax. Since Rmax is just a constant, we can pull it out of the summation. Note that the second factor is just a geometric series, and the geometric series evaluates to 1 divided by 1 minus gamma. Rmax times 1 divided by 1 minus gamma is finite and is an upper bound on gt. So, we know gt is finite. Now let's look at the effect of the discount factor on the behavior of the agent. We can look at the two extreme cases, when gamma equals 0 and when gamma approaches 1. When gamma equals 0, the return is just the reward at the next time step. So the agent is short-sighted and only cares about immediate expected reward. On the other hand, when gamma approaches 1, the immediate and future rewards are weighted nearly equally in the return. The agent in this case is more far-sighted. Finally, let's discuss a simple but important property of the return. It can be written recursively. Let's factor out gamma, starting from the second term in our sum. Amazingly, the sequence in parentheses is the return on the next time step. So we can just replace it with gt plus 1. Now we have a recursive equation with gt on the left and gt plus 1 on the right. This simple equation is more powerful than it seems. In future videos, we'll exploit this equation to design learning algorithms. To recap, we learned about continuing tasks where the agent-environment interaction goes on indefinitely, discounting is used to ensure returns are finite, and we saw that returns can be defined recursively. See you next time. When should we formulate a problem as an episodic or a continuing task? In this short video, we'll discuss a few more examples that will help us understand episodic and continuing problems. By the end of this video, you will be able to understand when to formalize a task as episodic or continuing. First, let's look at an example of an episodic task. Consider an agent learning to play a simple video game. The player, represented in blue, gets points for collecting white treasure blocks. The game ends when the player touches a green enemy block. This game is naturally represented as an episodic MDP. The agent tries to get a high score, collecting as many points as possible before the game ends. The state is an array of pixel values corresponding to the current screen. There are 4 actions: up, down, left, and right. The agent gets a reward of +1 whenever it collects a treasure block. And an episode ends when the agent touches one of the green enemies. Regardless of how the episode ends, the next episode will begin with the agent in the center of the screen with no enemies present. By the way, the agent you are currently watching was trained with Q-learning. It's pretty good at this game, isn't it? In Course 2, you'll learn about this algorithm and implement it yourself.
Now let's look at an example of a continuing task. The agent is going to schedule jobs on a set of servers. Suppose we have 3 servers used by reinforcement learning researchers to run experiments. Researchers submit jobs with different priorities to a single queue. The state is the number of free servers and the priority of the job at the top of the queue. The actions are to reject or accept the job at the top of the queue if a server is free. Accepting the job runs it and yields a reward equal to the job's priority. Rejecting a job yields a negative reward proportional to the priority and sends the job to the back of the queue. The agent should be careful about scheduling low priority jobs since it could prevent high priority jobs from being scheduled later. The servers become available as they finish their jobs. The researchers continually add jobs to the queue, and the agent accepts or rejects them. Since this process never stops, it's well described as a continuing task. That's it for this video. You've now seen some concrete examples of episodic and continuing tasks. Episodic tasks break naturally into independent episodes. Continuing tasks are assumed to continue indefinitely. You should now be able to determine which formulation is most appropriate for a given problem. This week, we introduced MDPs. When you first heard about MDPs, you might have thought, how can this be the problem formulation used for all of reinforcement learning? It's too simple. By now, maybe you're starting to see that it can represent many problems. To recap, MDPs formalize the problem of an agent interacting with an environment. The agent and environment interact at discrete time steps. At each time, the agent observes the current state of the environment. Based on this state, the agent selects an action. After that, the environment transitions to a new state and emits a reward. Remember, the agent's choices have long-term consequences. The action it selects influences future states and rewards. The goal of reinforced learning is to maximize total future reward. This often means balancing immediate reward with the long-term consequences of actions. We formalize this goal with the expected return, which is the expected discounted sum of future rewards. By discounting with gamma less than 1, we can guarantee the return remains finite. The precise value of gamma defines how much we care about short-term rewards versus long-term rewards. We discussed a number of examples of problems that can be naturally formulated as either episodic or continuing MDPs. The MDP formalism can be used to model many real-world problems. The first step in applying reinforcement learning will always be to formulate the problem as an MDP. That's all for this week. See you next time.
Reinforcement learning is a problem formulation for sequential decision-making under uncertainty. Earlier, we learned that the agent's role in this interaction is to choose an action on each time step. The choice of action has an immediate impact on both the immediate reward and the next state. In this video, we will describe policies, how an agent selects these actions. By the end of this video, you will be able to recognize that a policy is a distribution over actions for each state, describe the similarities and differences between stochastic and deterministic policies, and generate valid policies for a given MDP or Markov decision process. In the simplest case, a policy maps each state to a single action. This kind of policy is called a deterministic policy. We will use the fancy Greek letter pi to denote a policy. Pi of s represents the action selected in state s by the policy pi. In this example, pi selects the action A1 in state S0 and action A0 in states S1 and S2. We can visualize a deterministic policy with a table. Each row describes the action chosen by pi in each state. Notice that the agent can select the same action in multiple states. And some actions might not be selected in any state. Consider the example shown here, where an agent moves towards its house on a grid. The states correspond to the locations on the grid. The actions move the agent up, down, left and right. The arrows describe one possible policy, which moves the agent towards its house. Each arrow tells the agent which direction to move in each state. In general, a policy assigns probabilities to each action in each state. We use the notation pi of A given S to represent the probability of selecting action A in a state S. A stochastic policy is one where multiple actions may be selected with non-zero probability. Here we show the distribution over actions for state S0 according to pi. Remember that pi specifies a separate distribution over actions for each state. So we have to follow some basic rules. The sum over all action probabilities must be 1 for each state. And each action probability must be non-negative. Let's look at another state, S1. Pi in S1 corresponds to a completely different distribution over actions. In this example, the set of available actions is the same in each state. But in general, this set can be different in each state. Most of the time, we won't need this extra generality, but it's important nonetheless. Let's go back to our house example. A stochastic policy might choose up or right with equal probability in the bottom row. Notice this stochastic policy will take the same number of steps to reach the house as the deterministic policy we discussed before. Previously, we discussed how a stochastic policy, like epsilon greedy, can be useful for exploration. The same kind of exploration-exploitation trade-off exists in MDPs. Let's talk more about that later. It's important that policies depend only on the current state, not on other things like time or previous states. The state defines all the information used to select the current action. In this MDP, we can define a policy that chooses to go either left or right with equal probability. We might also want to define a policy that chooses the opposite of what it did last, alternating between left and right actions. However, that would not be a valid policy because this is conditional on the last action. That means the action depends on something other than the state. It is better to think of this as a requirement on the state, not a limitation on the agent. In MDPs, we assume that the state includes all the information required for decision making. If alternating between left and right would yield a higher return, then the last action should be included in the state. That's it for this video. The most important things to remember are: 1. An agent's behavior is specified by a policy that maps the state to a probability distribution over actions. And 2. The policy can depend only on the current state and not other things like time or previous states. See you next time. Many problems involve some amount of delayed reward. A store manager could lower their prices and sell off their entire inventory to maximize short-term gain. But they would do better in the long run by maintaining inventory to sell when the demand is high. In reinforcement learning, reward captures the notion of short-term gain. The objective, however, is to learn a policy that achieves the most reward in the long run. Value functions formalize what this means. By the end of this video, you will be able to describe the roles of the state value and action value functions in reinforcement learning, describe the relationship between value functions and policies, and create examples of value functions for a given MDP. Roughly speaking, a state value function is the future reward an agent can expect to receive starting from a particular state. More precisely, the state value function is the expected return from a given state. The agent's behavior will also determine how much total reward it can expect. So a value function is defined with respect to a given policy. The subscript pi indicates the value function is contingent on the agent selecting actions according to pi. Likewise, a subscript pi on the expectation indicates that the expectation is computed with respect to the policy pi. We can also define an action value function. An action value describes what happens when the agent first selects a particular action. More formally, the action value of a state is the expected return if the agent selects action A and then follows policy pi. Value functions are crucial in reinforcement learning. They allow an agent to query the quality of its current situation instead of waiting to observe the long-term outcome. The benefit is twofold. First, the return is not immediately available, and second, the return may be random due to stochasticity in both the policy and environment dynamics. The value function summarizes all the possible futures by averaging over returns. Ultimately, we care most about learning a good policy. Value functions enable us to judge the quality of different policies. For example, consider an agent playing the game of chess. Chess is an episodic MDP. The state is given by the positions of all the pieces on the board. The actions are the legal moves. And termination occurs when the game ends in either a win, loss, or draw. We could define the reward as +1 for winning and 0 for all the other moves. This reward does not tell us much about how well the agent is playing during the match. We will have to wait until the end of the game to see any non-zero reward. The value function tells us much more. The state value is equal to the expected sum of future rewards. Since the only possible non-zero reward is +1 for winning, the state value is simply the probability of winning if we follow the current policy pi. In this two-player game, the opponent's move is part of the state transition. For example, the environment moves both the agent's piece, circled in blue, and the opponent's piece, circled in red. This puts the board into a new state, S'. Note, the value of state S' is lower than the value of state S. This means we are less likely to win the game from this new state, assuming we continue following policy pi. An action value function would allow us to assess the probability of winning for each possible move, given we follow the policy pi for the rest of the game. To build some intuition, let's look at a simple continuing MDP. The states are defined by the locations on the grid. The actions move the agent up, down, left, or right. The agent cannot move off the grid, and bumping generates a reward of -1. Most other actions yield no reward. There are two special states, however. These special states are labeled A and B. Every action in state A yields +10 reward and +5 reward in state B. Every action in state A and B transitions the agent to states A' and B' respectively. Remember, we must specify the policy before we can figure out what the value function is. Let's look at the uniform random policy. Since this is a continuing task, we need to specify gamma. Let's go with 0.9. Later, we will learn several ways to compute and estimate the value function. But this time we'll be nice to you and compute it for you. On the right, we have written the value of each state. First, notice the negative values near the bottom. These values are low because the agent is likely to bump into the wall before reaching the distant states A and B. Remember, A and B are both the only sources of positive reward in this MDP. State A has the highest value. Notice that the value is less than 10, even though every action from state A generates a reward of +10. Why? Because every transition from A moves the agent close to the lower wall. And near the lower wall, the random policy is likely to bump and get negative reward. On the other hand, the value of state B is slightly greater than 5. The transition from B moves the agent to the middle. In the middle, the agent is unlikely to bump and is close to the high-valued states A and B. It's really quite amazing how the value function compactly summarizes all these possibilities. In this video, we introduce the definitions of state and action value functions. Soon, we will discuss how value functions can be computed. For now, you should understand that a state value function refers to the expected return from a given state under a specific policy, and an action value function refers to the expected return from a given state after selecting a particular action and then following a given policy.
I'm Andy Bartow, and I want to introduce Rich Sutton, who was my first student, and we spent many years working together, and both of us are amazed, I think, to the outgrowth of that early work. And Rich is an amazingly focused, persistent, man of genius, I think, and see, I'm embarrassing him. You know, a lot of the core ideas are really owe an enormous amount to Rich. So that's Rich.
Well, I feel I've learned an enormous amount from you, Andy, and you've just been essential to making our work scholarly and relevant to, well, to the modern age and to the old. I feel enormously grounded by all the things I learned as your student in those years. But I want to say that the main thing we did, well, we wrote that textbook, okay, but the main thing we did was we rediscovered the field of reinforcement learning. Sometimes like to say that we discovered it, but I know that you would react to that because nothing is new. There's nothing new under the sun, you used to tell me.
Pretty much.
And if you do find something, there's nothing wrong with rediscovering something old. You should embrace that, and if you rediscover the wheel, as you say, we should call it the wheel.
Maybe a better wheel.
Maybe a better wheel. But I do feel we rediscovered reinforcement. We woke it up because it had fallen into neglect, and we clarified what it was and how it was different from supervised learning. And this is sort of, you know, what I was characterizing as the origin story of reinforcement learning. It was an obvious idea. Marvin Minsky knew it in 1960 or 59, and it's so obvious that everyone knew it, but then it became overshadowed by supervised learning until Harry Clough, you know, started knocking on people's doors and saying, hey, this is something that's been neglected and is real and it's important, and he tasked us to figure it out.
So in fact, the very first neural network simulation on a digital computer by Farley and Clark was
1954.
was a reinforcement learning system. And their second paper, Clark and Farley, a year later or something, was the same system, but they focused on generalization and, you know, it departed from the roots of it. And after that, you know, perceptron and Woodrow-Hoff was error correction. Even though some of the words they used were trial and error, they really weren't. So
Became supervised.
yeah.
Yeah.
And there were exceptions, but you know, as Rich said, Minsky's thesis and his STEPS paper is full of, you know, prediction, TD-like things, certainly the credit assignment problem, and then his thesis at Princeton was a reinforcement learning physical network that learned to go through a maze. I think Minsky lost interest in it for a number of reasons, but or maybe was embarrassed by it. I don't know, but that was a reinforcement learning system.
So Andy, typical of yourself, you are talking about what other people did historically, but maybe typical of me, I wanted to bring it back to what we did, because I think we did do something. We almost did very little, but we recognized. We just stood up and said, this is a thing. This is a thing that hasn't been investigated, and it's deserving of investigation. And we wrote papers on associative search networks and just really, really simple ideas, and made the claim that this had not been done, that a combination of association and trial and error. As you said, I think at the time, you know, search for something that works, and then you remember. Combining search and memory, and that is the essence of reinforcement, and that strangely had been lost.
So I discovered something relevant to that. Memoization, that Robin Popplestone, who was my colleague at University of Massachusetts for a while, and Donald Mickey talked about memoization, which is what RL is, memoized search. You do some operation, and then you remember the results, and the next time you have to do it, you look it up instead of recomputing it, and it saves a lot of time and so on. And in a sense, RL at its root is memoized context-sensitive search.
Yeah. Yeah.
And Popplestone actually at the end of one of his paper on this, 50, I forget the date, but talks about interpolating, like using polynomials instead of lookup table to look up, something, and with generalization, and that's, what neural networks do, for example. So we didn't really
Rediscovered.
We didn't invent memoization, but we sort of a new use for it. I don't know if people were doing memoized search the way reinforcement learning does.
So Harry had his idea of a distributed approach, goal-seeking systems made up of goal-seeking components. And he also had the idea of what he called generalized reinforcement, that one of these units could be reinforced by all kinds of signals, not just by any signal. And the way I remember it, the essential, I don't know, I'm going to call it, so it's like an insight, but it's like an absence of insight. We decided one day, well, maybe just the goal-seeking unit thing, maybe that's an interesting idea all on its own, without making goal-seeking systems out of goal-seeking components, and without having generalized reinforcement. What if we just have a specialized reward signal, and we just study that learning, and maybe that's a thing. Maybe that's something that needs to be worked out. To me, it was very much like maybe just that. It was like leave all that other fancy stuff or confusing stuff aside for the moment. There's a point to be made, and I think that's what reinforcement learning is. It's just focusing on a learning system that actually wants something, that does trial and error and remembers it, and it has a specialized reward signal.
In everyday life, we learn a lot without getting explicit, positive, or negative feedback. Imagine, for example, you are riding a bike and hit a rock that sends you off balance. Let's say you recover so you don't suffer any injury. You might learn to avoid rocks in the future and perhaps react more quickly if you do hit one. How do we know that hitting a rock is bad even when nothing bad happened this time? The answer is that we recognize that the state of losing our balance is bad even without falling and hurting ourselves. Perhaps we had similar experiences in our past when things didn't work out so nicely. In reinforcement learning, a similar idea allows us to relate the value of the current state to the value of future states without waiting to observe all the future rewards. We use Bellman equations to formalize this connection between the value of a state and its possible successors. By the end of this video, you will be able to derive the Bellman equation for state value functions, define the Bellman equation for action value functions, and understand how Bellman equations relate current and future values. First, let's talk about the Bellman equation for the state value function. The Bellman equation for the state value function defines a relationship between the value of a state and the value of its possible successor states. Now we'll illustrate how to derive this relationship from the definitions of the state value function and return. Let's start by recalling that the state value function is defined as the expected return starting from the state S. Recall that the return is defined as the discounted sum of future rewards. We saw previously that the return at time t can be written recursively as the immediate reward plus the discounted return at time t plus 1. Now let's expand this expected return. First, we expand the expected return as a sum over possible action choices made by the agent. Second, we expand over possible rewards and next states conditioned on state S and action A. We can break it down in this order because the action choice depends only on the current state, while the next state and reward depend only on the current state and action. The result is a weighted sum of terms consisting of immediate reward plus expected future return from the next state S prime. All we have done is explicitly write the expectation as it's defined, as a sum of possible outcomes weighted by the probability that they occur. Note that capital RT plus 1 is a random variable, while the little r represents each possible reward outcome. The expected return depends on states and rewards infinitely far into the future. We could recursively expand this equation as many times as we want, but it would only make the expression more complicated. Instead, we can notice that this expected return is also the definition of the value function for state S prime. The only difference is that the time index is t plus 1 instead of t. This is not an issue because neither the policy nor p depends on time. Making this replacement, we get the Bellman equation for the state value function. The magic of value functions is that we can use them as a stand-in for the average of an infinite number of possible futures. We can derive a similar equation for the action value function. It will be a recursive equation for the value of a state-action pair in terms of its possible successor state-action pairs. In this case, the equation does not begin with the policy selecting an action. This is because the action is already fixed as part of the state-action pair. Instead, we skip directly to the dynamics function p to select the immediate reward and next state S prime. Again, we have a weighted sum over terms consisting of immediate reward plus expected future return given a specific next state little s prime. However, unlike the Bellman equation for the state value function, we can't stop here. We want a recursive equation for the value of one state action pair in terms of the next state action pair. At the moment, we have the expected return given only the next state. To change this, we can express the expected return from the next state as a sum over the agent's possible action choices. In particular, we can change the expectation to be conditioned on both the next state and the next action, and then sum over all possible actions. Each term is weighted by the probability under pi of selecting A prime in the state S prime. Now this expected return is the same as the definition of the action value function for S prime and A prime. Making this replacement, we get the Bellman equation for the action value function. So we have now covered how to derive the Bellman equations for state and action value functions. These equations provide relationships between the values of a state or state action pair and the possible next states or next state action pairs. You might be wondering why we care so much about these definitions and relationships. The Bellman equations capture an important structure of the reinforcement learning problem. Next, we will discuss why this relationship is so fundamental in reinforcement learning and how we can use it to design algorithms which efficiently estimate value functions. Previously, we learned how Bellman equations allow us to express the value of a state or state action pair in terms of its possible successors. But you may be wondering, what is the point of all this? By the end of this video, you will be able to use the Bellman equations to compute value functions. To illustrate the power of Bellman equations, consider this small example consisting of just 4 states labeled A, B, C, and D on a grid. The action space consists of moving up, down, left, or right. Actions which would move off the grid instead keep the agent in place. Say, for example, we start in state C. Moving up would take us to state A. If we then try to move left, we would hit a wall and stay in state A. Moving right next would take us to state B. From there, moving down would land us in state D. The reward is 0 everywhere, except for any time the agent lands in state B. If the agent lands in state B, it gets a reward of +5. This includes starting in state B and hitting a wall to remain there. Let's consider the uniform random policy, which moves in every direction 25% of the time. The discount factor gamma is 0.7. How can we actually work out the value of each of these states, A, B, C, and D, under this policy? Recall that the value function is defined as the expected return under policy pi. This is an average over the return obtained by each sequence of actions an agent could possibly choose, infinitely many possible futures. Luckily, the Bellman equation for the state value function provides an elegant solution. Using the Bellman equation, we can write down an expression for the value of state A in terms of a sum over the 4 possible actions and the resulting possible successor states. We can simplify the expression further in this case because for each action, there's only one possible associated next state and reward. Thus, the sum over S prime and R reduces to a single value. Note that here, S prime and R do still depend on the selected action and the current state S. But to keep the notation short, we haven't written this explicitly. If we go right from state A, we land in state B and receive a reward of +5. This happens 1/4 of the time under the random policy. If we go down, we land in state C and receive no immediate reward. Again, this occurs 1/4 of the time. If we go either up or left, we will land back in state A again. Each of the actions up and left again occur 1/4 of the time. Since they both land in state A and receive no reward, we combine them into a single term with a factor of 1/2. Finally, we arrive at the expression shown here for the value of state A. We can write down a similar equation for each of the other states, B, C, and D. Now we have a system of 4 equations for 4 variables. You can solve this by hand if you want, or put it into an automatic equation solver. The unique solution is shown here. The important thing to note is that the Bellman equation reduced an unmanageable infinite sum over possible futures to a simple linear algebra problem. Perhaps for this small problem, you can come up with other ways to work out the values of each of these states. However, the Bellman equation provides a powerful general relationship for MDPs. In this case, we use the Bellman equation to directly write down a system of equations for the state values and then solve the system to find the values. This approach may be possible for MDPs of moderate size. However, in more complex problems, this won't always be practical. Consider the game of chess, for example. We probably won't be able to even list all the possible states. There are around 10 to the 45 of them. Constructing and solving the resulting system of Bellman equations would be a whole other story. Yet humans can learn to play chess very well. However, this simple game represents a tiny fraction of human experience, and humans can learn to do many things. Our agents should be able to learn many things too. In upcoming lessons, we will discuss algorithms based on Bellman equations that can scale up to large problems. Hopefully, you see why Bellman equations are so fundamental for reinforcement learning. To sum up, without the Bellman equation, we might have to consider an infinite number of possible futures. The Bellman equations exploit the structure of the MDP formulation to reduce this infinite sum to a system of linear equations. We can then potentially solve the Bellman equation directly to find the state values. Up to this point, we've generally talked about a policy as something that is given. The policy specifies how an agent behaves. Given this way of behaving, we then aim to find the value function. But the goal of reinforcement learning is not just to evaluate specific policies. Ultimately, we want to find a policy that obtains as much reward as possible in the long run. In this video, we will make this notion precise with the idea of an optimal policy. By the end of this video, you will be able to define an optimal policy, understand how a policy can be at least as good as every other policy in every state, and identify an optimal policy for a given MDP. To define an optimal policy, we first have to understand what it means for one policy to be better than another. Here we can see the value of two policies plotted across states. Note that we plotted as a continuous line for illustration only. We are still considering discrete states, and the value might not vary smoothly across states. This plot illustrates that in some states, pi1 achieves a higher value, and in other states, pi2 achieves a higher value. So it does not make much sense to say pi1 is better than pi2, or that pi2 is better than pi1. We will say policy pi1 is as good as or better than policy pi2 if and only if the value under pi1 is greater than or equal to the value under pi2 for every state. We denote this relationship between policies with a greater than or equal to sign. In the diagram shown here, the line visualizing the value of pi1 is always above the line for pi2. So in this case, pi1 is as good as or better than pi2. An optimal policy is a policy which is as good as or better than all the other policies. That is, an optimal policy will have the highest possible value in every state. There is always at least one optimal policy, but there may be more than one. We'll use the notation pi star to denote any optimal policy. It might not be clear why there must exist optimal policies. That is, policies that are at least as good as all other policies in every state. Couldn't we have a situation where doing well in one state requires doing badly in another? Let's say there is such a policy pi1, which does well in some states, while policy pi2 does well in others. We could combine these policies into a third policy pi3, which always chooses actions according to whichever of policy pi1 and pi2 has the highest value in the current state. Pi3 will necessarily have a value greater than or equal to both pi1 and pi2 in every state. So we will never have a situation where doing well in one state requires sacrificing value in another. Because of this, there always exists some policy which is best in every state. This is of course only an informal argument, but there is in fact a rigorous proof showing that there must always exist at least one optimal deterministic policy. Notice that in some states, pi3 has a strictly greater value than either pi1 or pi2. As an exercise, try to explain how this is possible given that pi3 simply chooses actions according to whichever of pi1 and pi2 has a higher value in each state. Let's look at a specific example to build some intuition about optimal policies. Consider the two-choice MDP shown here. The only decision to be made is in the top state labeled X. The agent can take either action A1 or A2. From state X, action A1 takes the agent to state Y. In state Y, only action A1 is available, and it takes the agent back to state X. On the other hand, action A2 and X takes the agent to state Z. From state Z, action A1 is again the only action available, and it takes the agent back to state X. The numbers show the rewards the agent receives after each action. Notice that while A1 offers an immediate reward of +1, A2 offers a larger reward of +2 after a single step delay. There are only two deterministic policies in this MDP, which are completely defined by the agent's choice in state X. Take action A1 or take action A2. Let's call these pi1 and pi2. Which of these two policies is optimal? The optimal policy will be the one for which the value of X is highest. The answer depends on the discount factor gamma. Consider gamma equals 0. In this case, the value is defined using only the immediate reward. The value of state X under pi1 is +1, while the value under pi2 is 0 because the +2 reward occurs after a one-step delay, which does not affect the return when gamma is set to 0. So in this case, pi1 is the optimal policy. What if instead gamma equals 0.9? In this case, the value of X under each policy is an infinite sum. Pi1 receives an immediate reward of 1, followed by 0, and then 1 again, and so on. Each reward in the expression for the value of state X is discounted by some power of gamma.
We can express this compactly as a geometric series. Applying the geometric series formula, we get the value shown here for pi 1, which evaluates to around 5.3. We can write the value under pi 2 similarly, except we will receive a reward of 2 on every odd step instead of 1 on every even step. We can again write this as a geometric series and obtain a closed form solution. In this case, the solution evaluates to around 9.5. Since 9.5 is higher than 5.3, pi 2 is optimal in this case. In this two-choice MDP, finding the optimal policy was relatively straightforward. There were only 2 deterministic policies, and we simply had to compute the value function for each of them. In general, it will not be so easy. Even if we limit ourselves to deterministic policies, the number of possible policies is equal to the number of possible actions to the power of the number of states. We could use a brute force search where we compute the value function for every policy to find the optimal policy, but it's not hard to see this will become intractable for even moderately large MDPs. Luckily, there's a better way to organize our search of the policy space. The solution will come in the form of yet another set of Bellman equations called the Bellman optimality equations, which we will introduce in an upcoming video. That's it for this video. The most important things to take away are an optimal policy is defined as the policy with the highest value in all states. At least one optimal policy always exists, but there may be more than one. The exponential number of possible policies makes searching for the optimal policy by brute force intractable. Previously, we learned about how optimal policies achieve the goal of reinforcement learning, to obtain as much reward as possible in the long run. In this video, we'll describe the related notion of an optimal value function and introduce an associated set of Bellman equations. By the end of this video, you will be able to derive the Bellman optimality equation for the state value function, derive the Bellman optimality equation for the action value function, and understand how the Bellman optimality equations relate to the previously introduced Bellman equations. Recall that for 2 policies, pi 1 and pi 2, pi 1 is considered as good as or better than pi 2 if and only if the value under pi 1 is greater than or equal to the value under pi 2 for all states. An optimal policy is one which is good as or better than every other policy. The value function for the optimal policy thus has the greatest value possible in every state. We can express this mathematically by writing that v pi star of s is equal to the maximum value over all policies. And this holds for every state in our state space. Taking a maximum over policies might not be intuitive, so let's take a moment to break down what it means. Imagine we were to consider every possible policy and compute each of their values for the state s. The value of an optimal policy is defined to be the largest of all the computed values. We could repeat this for every state, and the value of an optimal policy would always be the largest. All optimal policies have this same optimal state value function, which we denote by v star. Optimal policies also share the same optimal action value function, which is again the maximum possible for every state action pair. We denote this shared action value function by q star. Recall the Bellman equation for the state value function. This equation holds for the value function of any policy, including an optimal policy. By substituting the optimal policy pi star into this Bellman equation, we get the Bellman equation for v star. So far, we haven't done anything special. This is simply the Bellman equation we introduced previously for the specific case of an optimal policy. However, because this is an optimal policy, we can rewrite the equation in a special form which doesn't reference the policy itself. Remember, there always exists an optimal deterministic policy, one that selects an optimal action in every state. Such a deterministic optimal policy will assign probability 1 for an action that achieves the highest value and probability 0 for all other actions. We can express this another way by replacing the sum over pi star with a max over a. Notice that pi star no longer appears in the equation.
we have derived a relationship that applies directly to V star itself. We call this special form the Bellman optimality equation for V star. We can make the same replacement in the Bellman equation for the action value function. Here, the optimal policy appears in the inner sum. Once again, we replace the sum over pi star with the max over A. This gives us the Bellman optimality equation for Q star. In an earlier lecture, we discussed how the Bellman equations form a linear system of equations that can be solved by standard methods. The Bellman optimality equation gives us a similar system of equations for the optimal value. One natural question is, can we solve this system in a similar way to find the optimal state value function? Unfortunately, the answer is no. Taking the maximum over actions is not a linear operation, so standard techniques from linear algebra for solving linear systems won't apply. In this course, we will not form and solve systems of equations in the usual way. Instead, we will use other techniques based on the Bellman equations to compute value functions and policies. You might be wondering why we can't simply use pi star in the ordinary Bellman equation to get a system of linear equations for V star. The answer is simple. We don't know pi star. If we did, then we would have already achieved the fundamental goal of reinforcement learning. If we can manage to solve the Bellman optimality equation for V star, we can use the result to obtain pi star fairly easily. We will see how this can be done in the next video. So, we introduced optimal value functions and derived the associated Bellman optimality equations. The Bellman optimality equations relate the value of a state or state-action pair to its possible successors under any optimal policy. See you next time, where we'll learn how to find the optimal policy from the optimal value function.
This week we learned all about policies, value functions, and the relationships between them. We also learned about Bellman equations, which help us reason about the value of policies. In this video, we'll do a quick recap of everything we covered. Policies tell an agent how to behave. Deterministic policies map each state to an action. Each time a state is visited, a deterministic policy selects the associated action pi of s. Stochastic policies map each state to a distribution over all possible actions. Each time a state is visited, a stochastic policy randomly draws an action from the associated distribution with probability pi of a given s. A policy by definition depends only on the current state. It cannot depend on things like time or previous states. This is best thought of as a restriction on the state, not the agent. The state should provide the agent with all the information it needs to make a good decision. This is an important assumption for many of the techniques in reinforcement learning. Value functions are like magic. Value functions capture the future total reward under a particular policy. We discussed two kinds of value functions, state value functions and action value functions. The state value function gives the expected return from the current state under a policy. The action value function gives the expected return from state S if the agent first selects action A and follows pi after that. Value functions simplify things by aggregating many possible future returns into a single number. Bellman equations define a relationship between the value of a state or state-action pair and its successor states. The Bellman equation for the state value function gives the value of the current state as a sum over the values of all the successor states and immediate rewards. The Bellman equation for the action value function gives the value of a particular state-action pair as the sum over the values of all possible next state-action pairs and rewards. The Bellman equations can be directly solved to find the value function. These Bellman equations help us evaluate policies, but they do not yet achieve our ultimate goal, to find a policy that obtains as much reward as possible. To make this goal more precise, we defined optimal policies, the optimal value function, and the associated Bellman optimality equations. An optimal policy is a policy which achieves the highest value possible in every state. There is always at least one optimal policy, but there may be more than one. The optimal state value function is equal to the highest possible value in every state. Every optimal policy shares the same optimal state value function. The same is true for optimal action value functions and optimal policies. Like all value functions, the optimal value functions have Bellman equations. These Bellman equations do not reference a specific policy. This amounts to replacing the policy in the Bellman equation with a max over all actions. The optimal policy must always select the best available action. We can extract the optimal policy from the optimal state value function, but to do so, we also need the one-step dynamics of the MDP. We can get the optimal policy with much less work if we have the optimal action value function. We simply select the action with the highest value in each state. Next week, we will see how to compute optimal policies using these Bellman equations. See you then.
We often talk about two distinct tasks, policy evaluation and control. Policy evaluation is the task of determining the value function for a specific policy. Control is the task of finding a policy to obtain as much reward as possible. In other words, finding a policy which maximizes the value function. Control is the ultimate goal of reinforcement learning. But the task of policy evaluation is usually a necessary first step. It's hard to improve our policy if we don't have a way to assess how good it is. This week, we will look at a collection of algorithms called dynamic programming for solving both policy evaluation and control problems. By the end of this video, you will be able to understand the distinction between policy evaluation and control and explain the setting in which dynamic programming can be applied as well as its limitations. Dynamic programming algorithms use the Bellman equations to define iterative algorithms for both policy evaluation and control. Before diving into the details of this approach, let's take some time to clarify the two tasks. Imagine someone hands you a policy, and your job is to determine how good that policy is. Policy evaluation is the task of determining the state value function vpi for a particular policy pi. Recall that the value of a state under a policy pi is the expected return from that state if we act according to pi. The return is itself a discounted sum of future rewards. We have seen how the Bellman equation reduces the problem of finding vpi to a system of linear equations, one equation for each state. So, the problem of policy evaluation reduces to solving this system of linear equations. In principle, we could approach this task with a variety of methods from linear algebra. In practice, the iterative solution methods of dynamic programming are more suitable for general MDPs. Control is the task of improving a policy. Recall that a policy pi 2 is considered as good as or better than pi 1 if the value under pi 2 is greater than or equal to the value under pi 1 in every state. We say pi 2 is strictly better than pi 1 if pi 2 is as good as or better than pi 1 and there is at least one state where the value under pi 2 is strictly greater than the value under pi 1. The goal of the control task is to modify a policy to produce a new one which is strictly better. Moreover, we can try to improve the policy repeatedly to obtain a sequence of better and better policies. When this is no longer possible, it means there's no policy which is strictly better than the current policy. And so the current policy must be equal to an optimal policy, and we can consider the control task complete. Imagine we had access to the dynamics of the environment, P. This week is all about how we can use this knowledge to solve the tasks of policy evaluation and control. Even with access to these dynamics, we'll need careful thought and clever algorithms to compute value functions and optimal policies. For the next several videos, we will investigate a class of solution methods called dynamic programming for this purpose. Dynamic programming uses the various Bellman equations we've seen, along with knowledge of P, to work out value functions and optimal policies. Classical dynamic programming does not involve interaction with the environment at all. Instead, we use dynamic programming methods to compute value functions and optimal policies given a model of the MDP. Nonetheless, dynamic programming is very useful for understanding other reinforced learning algorithms. Most reinforced learning algorithms can be seen as an approximation to dynamic programming without the model. This connection is perhaps most striking in the temporal difference-based DYNA planning algorithm that we cover in Course 2. We will revisit these connections throughout this specialization. To summarize, policy evaluation is the task of determining the state value function vpi for policy pi. Control is the task of improving an existing policy. And dynamic programming techniques can be used to solve both of these tasks if we have access to the dynamics function p. See you next time, where we will learn how to use dynamic programming for policy evaluation. Dynamic programming algorithms are obtained by turning the Bellman equations into update rules. In this video, we will introduce the first of these algorithms, called iterative policy evaluation. By the end of this video, you will be able to outline the iterative policy evaluation algorithm for estimating state values for a given policy and apply iterative policy evaluation to compute value functions. Remember, the Bellman equation gives us a recursive expression for v pi. The idea of iterative policy evaluation is so simple that at first it might seem a bit silly. We take the Bellman equation and directly use it as an update rule. Now, instead of an equation which holds for the true value function, we have a procedure we can apply to iteratively refine our estimate of the value function. This will produce a sequence of better and better approximations to the value function. Let's see visually how this procedure works. We begin with an arbitrary initialization for our approximate value function. Let's call this v0. Each iteration then produces a better approximation by using the update rule shown at the top of the slide. Each iteration applies this update to every state S in the state space, which we call a sweep. Applying this update repeatedly leads to a better and better approximation to the state value function v pi. If this update leaves the value function approximation unchanged, that is, if vk plus 1 equals vk for all states, then vk equals v pi and we have found the value function. This is because v pi is the unique solution to the Bellman equation. The only way the update could leave vk unchanged is if vk already obeys the Bellman equation. In fact, it can be proven that for any choice of v0, vk will converge to v pi in the limit as k approaches infinity. To implement iterative policy evaluation, we store two arrays. Each has one entry for every state. One array, which we label v, stores the current approximate value function. Another array, v prime, stores the updated values. By using two arrays, we can compute the new values from the old, one state at a time, without the old values being changed in the process. At the end of a full sweep, we can write all the new values into v. Then we do the next iteration. It is also possible to implement a version with only one array, in which case some updates will themselves use new values instead of old. This single array version is still guaranteed to converge, and in fact will usually converge faster. This is because it gets to use the updated values sooner. But for simplicity, we focus on the two-array version. Let's look at how iterative policy evaluation works on a particular example. Consider the 4x4 grid world shown here. This is an episodic MDP with the terminal state located in the top left and bottom right corners. The terminal state is shown in two places, but formally it is the same state. The reward will be -1 for every transition. Since the problem is episodic, let's consider the undiscounted case of gamma equals 1. There are 4 possible actions in each state: up, down, left, and right. Each action is deterministic. If the action would move the agent off the grid, it instead leaves the agent in the same state. Now let's evaluate the uniform random policy, which selects each of the 4 actions 1/4 of the time. The value function represents the expected number of steps until termination from a given state. The order we sweep through the states is not important, since we are using the 2-array version of the algorithm. Let's assume we sweep the states first from left to right, and then from top to bottom. We never update the value of the terminal state, as it is defined to be 0. We initialize all the values in V to 0. The initial values stored in V' are irrelevant, since they will always be updated before they are used. We can now begin our first iteration with the update to state 1. To compute the update, we have to sum over all actions. Consider the left action first, which has probability 1/4 under the uniform random policy. The dynamics function p is deterministic here, so only the reward and value for 1s' contributes to the sum. The sum includes -1 for the reward and 0 for the value of the terminal state. Since we initialized all state values to 0, and the reward for each transition is -1, the computation for all the other actions will look much the same. The result is that V' of state 1 is set to -1. Next, we move to state 2. We first evaluate the term in the sum for the left action. Again, the action probability is 1/4, and in this case, the next state is state 1. Although we have updated the value of state 1 already, the version of the algorithm we are running will use the old value stored in V. So the value for state 1 in the update is still 0. Again, all the other actions will look much the same. The result is that V' of state 2 is also set to -1. In fact, since every state value is initialized to 0, every state's value will be set to -1. After completing this full sweep, we copy the updated values from V' to V. This has been only one sweep. Let's discuss now the full algorithm for iterative policy evaluation. Take any policy we want to evaluate. Initialize 2 arrays, V and V'. We can initialize these however we like, but let's set them to 0. We just saw how one sweep of iterative policy evaluation works. Let's look at how we compute multiple sweeps and determine how the algorithm stops. The outer loop continues until the change in the approximate value function becomes small. We track the largest update to the state value in a given iteration. Let's call this delta. The outer loop terminates when this maximum change is less than some user-specified constant called theta. As discussed before, once the approximate value function stops changing, we have converged to V'. Similarly, once the change in the approximate value function is very small, this means we are close to V'. Let's pick up where we left off in our grid world example. We had just completed our first sweep. Let's choose a value of 0.001 for the stopping parameter theta. The smaller the value we choose, the more accurate our final value estimate will be. We've already completed one iteration, and the maximum change in value was 1.0. Since this is greater than 0.001, we carry on to the next iteration. After the second sweep, notice how the terminal state starts to influence the value of the nearest states first. Let's run one more sweep. We see that now the influence of the terminal state has propagated further. Let's run a few more sweeps to see what happens. We can start to see how the value of each state is related to its proximity to the terminal state. Let's keep running until our maximum delta is less than theta. Here is the result we eventually arrive at. Our approximate value function has converged to the value function for the random policy. And we're done. That's it for this video. You should now understand how we can turn the Bellman equation into an update rule to iteratively compute value functions. Soon we will see how these ideas can also be used for policy improvement. See you next time! We just looked at how dynamic programming can be used to iteratively evaluate a policy. We hinted that this was the first step towards the control task, where the goal is to improve a policy. In this video, we'll finally explain how this works. By the end of this video, you will be able to understand the policy improvement theorem and how it can be used to construct improved policies, and use the value function for a policy to produce a better policy. Previously, we showed that given V star, we can find the optimal policy by choosing the greedy action. The greedy action maximizes the Bellman optimality equation in each state. Imagine instead of the optimal value function, we select an action which is greedy with respect to the value function v pi of an arbitrary policy pi. What can we say about this new policy that is greedy with respect to v pi? The first thing to note is that this new policy must be different than pi. If this greedification doesn't change pi, then pi was already greedy with respect to its own value function. This is just another way of saying that v pi obeys the Bellman optimality equation, in which case pi is already optimal. In fact, the new policy obtained in this way must be a strict improvement on pi unless pi was already optimal. This is a consequence of a general result called the policy improvement theorem. Recall the definition of Q pi. It tells you the value of a state if you take action A and then follow policy pi. Imagine we take action A according to pi prime and then follow policy pi. If this action has higher value than the action under pi, then pi prime must be better. The policy improvement theorem formalizes this idea. Policy pi prime is at least as good as pi if in each state the value of the action selected by pi prime is greater than or equal to the value of the action selected by pi. Policy pi prime is strictly better if the value is strictly greater in at least one state. Let's see how this works on the 4x4 grid world we used previously. Here's the final value function we found. Remember that this is the value function for the uniform random policy. Now, what might the greedified policy look like? In each state, we need to select the action that leads to the next state with the highest value. In this case, the value that is least negative. Here is pi prime. This is quite different from the uniform random policy we started with. Note that the values shown here do not correspond to the values for pi prime. The new policy is guaranteed to be an improvement on the uniform random policy we started with, according to the policy improvement theorem. In fact, if we look more closely at the new policy, we can see that it is in fact optimal. In every state, the chosen actions lie on a shortest path to the terminal state. Remember, the value function we started with was not the optimal value function, and yet the greedy policy with respect to v pi is optimal. More generally, the policy improvement theorem only guarantees that the new policy is an improvement on the original. We cannot always expect to find the optimal policy so easily. That's it for this video. You should now understand that the policy improvement theorem tells us that a greedified policy is a strict improvement unless the original policy was already optimal. You should also now know how to use the value function under a given policy to produce a strictly better policy. Next time, we will discuss how to use this result to create an iterative dynamic programming algorithm to find the optimal policy. See you then. We just learned how the value function computed for a given policy can be used to find a better policy. In this video, we will show how we can use this to find the optimal policy by iteratively evaluating and improving a sequence of policies. By the end of this video, you will be able to outline the policy iteration algorithm for finding the optimal policy, understand the dance of policy and value, how policy iteration reaches the optimal policy by alternating between evaluating a policy and improving it, and apply policy iteration to compute optimal policies and optimal value functions. Recall the policy improvement theorem. It tells us that we can construct a strictly better policy by acting greedily with respect to the value function of a given policy, unless the given policy was already optimal. Let's say we begin with the policy pi1. We can evaluate pi1 using iterative policy evaluation to obtain the state value v pi1. We call this the evaluation step. Using the results of the policy improvement theorem, we can then greedify with respect to v pi1 to obtain a better policy, pi2. We call this the improvement step. We can then compute v pi2 and use it to obtain an even better policy, pi3. This gives us a sequence of better and better policies. Each policy is guaranteed to be an improvement on the last unless the last policy was already optimal. So when we complete an iteration and the policy remains unchanged, we know we have found the optimal policy. At that point, we can terminate the algorithm. Each policy generated in this way is deterministic. There are a finite number of deterministic policies, so this iterative improvement must eventually reach an optimal policy. This method of finding an optimal policy is called policy iteration. Policy iteration consists of two distinct steps repeated over and over: evaluation and improvement. We first evaluate our current policy, pi1, which gives us a new value function that accurately reflects the value of pi1. The improvement step then uses v pi1 to produce a greedy policy, pi2. At this point, pi2 is greedy with respect to the value function of pi1, but v pi1 no longer accurately reflects the value of pi2. The next step, evaluation, makes our value function accurate with respect to the policy pi2. Once we do this, our policy is once again not greedy. This dance of policy and value proceeds back and forth until we reach the only policy which is greedy with respect to its own value function, the optimal policy. At this point, and only at this point, the policy is greedy and the value function is accurate. We can visualize this dance as bouncing back and forth between one line where the value function is accurate and another where the policy is greedy. These two lines intersect only at the optimal policy and value function. Policy iteration always makes progress towards the intersection by projecting first onto the line v equals v pi, and then onto the line where pi is greedy with respect to v. Of course, the real geometry of the space of policies and value functions is more complicated, but the same intuition holds. Here's what this procedure looks like in pseudocode. We initialize v and pi in any way we like for each state s. Next, we call iterative policy evaluation to make v reflect the value of pi. This is the algorithm we learned earlier in this module. Then in each state, we set pi to select the maximizing action under the value function. If this procedure changes the selected action in any state, we note that the policy is still changing and set policy stable to false. After completing step 3, we check if the policy is stable. If not, we carry on and evaluate the new policy. Let's look at how this works on a simple problem to build some intuition. Remember the 4x4 grid world example we used to demonstrate iterative policy evaluation. Previously, we showed that by evaluating the random policy and greedifying just once, we could find the optimal policy. This is not a very interesting case for policy iteration. Let's modify this problem a little bit to make the control task a bit harder. First, let's remove one of the terminal states so that there is only one way to end the episode. Previously, each state emitted a reward of -1. Instead, let's add some especially bad states. These bad states are marked in blue. Transitioning into them gives a reward of -10. The optimal policy should follow the winding low-cost path in white to the terminal state. This additional complexity means that policy iteration takes several iterations to discover the path. Let's see how this plays out. First, we initialize the policy and value function. As before, we choose the uniform random policy and set the value estimate to 0 for all states. The first step is to use iterative policy evaluation to evaluate the uniform random policy. Since we've seen how this works before, let's skip straight to the result. The values are quite negative everywhere, though slightly less so in states near the goal. Next, we perform the improvement step. You've seen how greedification works before, so again, let's skip to the result. Notice that near the terminal state, the policy correctly follows the low-cost path toward the terminal state. In the states in the bottom row, however, the policy instead takes the more direct but lower value path through the bad states. Let's evaluate this new policy. Notice how after just one improvement, the values are starting to look much more reasonable. But we aren't finished yet. Let's greedify again. Remember, the policy improvement theorem tells us that this new policy is an improvement on the last one, unless we have already reached the optimum. Specifically, the bottom right state now goes straight up along the low-cost path. One more step of policy evaluation reflects this change. The value of the bottom right state goes from -15 to just -6. Let's keep going until we reach the optimal policy. One more step of improvement improves action selection and yet another state. The next step of policy evaluation reflects this change. Improve again, and evaluate, and improve. Now we can see that the policy has reached the optimum and follows the low-cost path, avoiding the blue states. Evaluating one more time gives us the optimal value function. If we try to greedify again, the policy remains unchanged. This tells us that policy iteration is complete and the optimal policy has been found. This example shows the power of policy iteration, in that it guarantees we can follow a sequence of increasingly better policies until we reach an optimal policy. Policy iteration cuts through the search space, which is key when the optimal policy is not straightforward. In this case, literally. This same kind of complexity will come up in problems we really care about. In this week's assessment, you will have a chance to implement policy iteration on a slightly more realistic example. That's it for this video. You should now understand how policy iteration works by alternating between policy evaluation and policy improvement, and how policy iteration follows a sequence of better and better policies and value functions until it reaches the optimal policy and optimal value function. See you next time.
So far, we've presented policy iteration as a fairly rigid procedure. We alternate between evaluating the current policy and greedifying to improve the policy. The framework of generalized policy iteration allows much more freedom than this, while maintaining our optimality guarantees. In this video, we will outline some of these alternatives. By the end of this video, you'll be able to understand the framework of generalized policy iteration, outline value iteration, an important special case of generalized policy iteration, and differentiate synchronous and asynchronous dynamic programming methods. Recall the dance of policy and value. The policy iteration algorithm runs each step all the way to completion. Intuitively, we can imagine relaxing this. Imagine instead we follow a trajectory like this. Each evaluation step brings our estimate a little closer to the value of the current policy, but not all the way. Each policy improvement step makes our policy a little more greedy, but not totally greedy. Intuitively, this process should still make progress towards the optimal policy and value function. In fact, the theory tells us the same thing. We will use the term generalized policy iteration to refer to all the ways we can interleave policy evaluation and policy improvement. This brings us to our first generalized policy iteration algorithm, called value iteration. In value iteration, we still sweep over all the states and greedify with respect to the current value function. However, we do not run policy evaluation to completion. We perform just one sweep over all the states. After that, we greedify again. We can write this as an update rule which applies directly to the state value function. The update does not reference any specific policy, hence the name value iteration. The full algorithm looks very similar to iterative policy evaluation. Instead of updating the value according to a fixed policy, we update using the action that maximizes the current value estimate. Value iteration still converges to V star in the limit. We can recover the optimal policy from the optimal value function by taking the argmax. In practice, we need to specify a termination condition because we can't wait forever. We will use the same condition we used for policy evaluation. We simply terminate when the maximum change in the value function over a full sweep is less than some small value theta. Value iteration sweeps the entire state space on each iteration, just like policy iteration. Methods that perform systematic sweeps like this are called synchronous. This can be problematic if the state space is large. Every sweep could take a very long time. Asynchronous dynamic programming algorithms update the values of states in any order. They do not perform systematic sweeps. They might update a given state many times before another is updated even once. In order to guarantee convergence, asynchronous algorithms must continue to update the values of all states. Here, for example, the algorithm updates the same 3 states forever, ignoring all the others. This is not acceptable because the other states cannot be correct if they are never updated at all. Asynchronous algorithms can propagate value information quickly through selective updates. Sometimes this can be more efficient than a systematic sweep. For example, an asynchronous method can update the states near those that have recently changed value. That's it for this video. You should now understand that value iteration allows us to combine policy evaluation and improvement in a single step. Asynchronous dynamic programming methods give us freedom to update states in any order. And the idea of generalized policy iteration unifies many algorithms. This includes value iteration, asynchronous dynamic programming, and almost all the methods you will cover in this specialization. See you next time. We spent the last few videos discussing how dynamic programming methods can allow us to compute value functions and policies. But how useful are these methods really? How do they compare to simple alternatives? In this video, we will talk about some of the other possible solution strategies. By comparison, dynamic programming is actually surprisingly efficient. By the end of this video, you'll be able to describe Monte Carlo sampling as an alternative method for learning a value function, describe brute force search as an alternative method for finding an optimal policy, and understand the advantages of dynamic programming and bootstrapping over these alternatives. Iterative policy evaluation is the dynamic programming solution to the prediction or policy evaluation problem. Let's look at a sample-based alternative for policy evaluation. The value of each state can be treated as a totally independent estimation problem. First, recall that the value is the expected return from a given state. The procedure is simple. First, we gather a large number of returns under pi and take their average. This will eventually converge to the state value. This is called a Monte Carlo method. However, if we do it this way, we may need a large number of returns from each state. Each return depends on many random actions selected by pi, as well as many random state transitions due to the dynamics of the MDP. We could be dealing with a lot of randomness here. Each return might be very different than the true state value. So we may need to average many returns before the estimate converges. And we have to do this for every single state. The key insight of dynamic programming is that we do not have to treat the evaluation of each state as a separate problem. We can use the other value estimates we have already worked so hard to compute. This process of using the value estimates of successor states to improve our current value estimate is known as bootstrapping. This can be much more efficient than a Monte Carlo method that estimates each value independently. Policy iteration computes optimal policies. Brute force search is a possible alternative. This method simply evaluates every possible deterministic policy, one at a time. We then pick the one with the highest value. There are a finite number of deterministic policies, and there always exists an optimal deterministic policy. So brute force search will find the answer eventually. However, the number of deterministic policies can be huge. A deterministic policy consists of one action choice per state. So the total number of deterministic policies is exponential in the number of states. Even on a fairly simple problem, this number could be massive. This process could take a very long time. The policy improvement theorem guarantees that policy iteration will find a sequence of better and better policies. This is a significant improvement over exhaustively trying each and every policy. So how efficient is dynamic programming compared to these naive alternatives? Well, policy iteration is guaranteed to find the optimal policy in time polynomial in the number of states and actions. Thus, dynamic programming is exponentially faster than the brute force search of the policy space. In practice, dynamic programming is usually much faster even than this worst case guarantee. For example, the original 4x4 grid world converged in just one step of policy iteration. When we made the problem harder by adding bad states, it still converged in just 5 iterations. It might also seem restrictive that we have to run policy evaluation to completion for each step of policy iteration. In practice, this is not so bad. With each iteration, the policy tends to change less and less. The policy evaluation step changes the value function less, and thus, the evaluation step typically terminates quickly. Generally, solving an MDP gets harder as the number of states grows. The curse of dimensionality says that the size of the state space grows exponentially as the number of state variables increases. A single agent moving around a grid world is fine. But what if we wanted to coordinate a transportation network of thousands of drivers moving between hundreds of locations? A raw enumeration of the possible states could lead to an exponential blowup. Clearly, this would lead to problems if we try to sweep the states to perform policy iteration. In fact, this is not an issue with dynamic programming. This is a statement about the difficulty of the problems we are interested in tackling. Various techniques for mitigating this curse exist, and we will continue to deal with this curse for the remainder of our time together. That's it for this video. The most important takeaway is that bootstrapping can save us from performing a huge amount of unnecessary work by exploiting the connection between the value of a state and its possible successors. See you next time. This week, we learned all about dynamic programming and how it can be used to solve the tasks of policy evaluation and control. These algorithms form the foundation for reinforced learning algorithms that we will learn about later. In this video, we'll do a quick recap of everything we covered. Policy evaluation is the task of determining the state value function vpi for a particular policy pi. Iterative policy evaluation takes the Bellman equation for vpi and turns it into an update rule. It produces a sequence of better and better approximations to vpi. Control refers to the task of improving a policy. The policy improvement theorem tells us how to construct a better policy from a given policy. The new policy pi prime is produced by simply greedifying with respect to the current values. Pi prime is guaranteed to be strictly better than pi unless pi was already optimal. The dynamic programming algorithm for control is built on the policy improvement theorem. This algorithm is called policy iteration. Policy iteration consists of 2 steps, policy evaluation and policy improvement. In policy evaluation, we find the value function for the current policy. Policy improvement, or greedification, then makes the policy greedy with respect to the current value function. These steps are repeated over and over until the policy doesn't change, in which case the policy is guaranteed to be optimal. We also discussed the framework of generalized policy iteration. In generalized policy iteration, the evaluation and improvement steps need not run to completion. One example of generalized policy iteration is value iteration. Generalized policy iteration also includes asynchronous dynamic programming methods. Synchronous methods repeatedly sweep over the entire state space. Asynchronous methods are more flexible and they can update states in any order. Asynchronous methods can more efficiently propagate value information. This can be especially helpful when the state space is very large. Asynchronous methods can be designed to focus on a few relevant states. In dynamic programming, we, in some sense, assume the best possible situation. We know exactly how the MDP works, and yet it still took considerable thought and clever algorithms to efficiently compute optimal policies. We will continue to reap the benefits of this cleverness in almost all the algorithms we see in the remainder of this course. That brings us to the end of this course on the fundamentals of reinforcement learning. Congratulations! You now have a solid foundation to dive into the concepts and algorithms we'll cover in the rest of this specialization. We started off with an introduction to the idea of choosing actions to maximize reward in bandits. In bandits, we have a fixed set of actions, or arms, to choose from. Each action gives us a reward according to some unknown distribution. We would like to always pull the arm that provides the highest reward on average. Since we don't know the reward distributions initially, we have to try each arm many times to get an idea of each average. This brought us to the exploration-exploitation trade-off. Pull the arm that looks best now too much, and you might miss out on another, better arm that only appeared worse due to insufficient information. Spend too long exploring all the possibilities, and you might sacrifice exploiting an arm that you have good reason to believe has much higher value. We talked about various strategies to handle this trade-off. Dealing with bandits introduces many interesting questions, such as how to handle the exploration-exploitation trade-off. However, bandits don't include everything. The K-arm bandit problem presents the agent with the same situation at each time step. There is a single best action and no need to associate different actions to different situations. The impact of the agent's action selection is immediate, and the reward is not delayed. To better model the complexity of real-world problems, we introduced Markov decision processes, or MDPs. In MDPs, the action chosen by the agent impacts not only the immediate reward, but also the next state. In turn, this affects the potential for future reward. So actions can have a long-term consequence. We introduced the idea of return, which is a potentially discounted sum of future rewards. The MDP formalism can be used to model many interesting real-world problems. The solution methods we explore in this specialization will be applicable to a broad range of problems. The first step is always to frame your problem as an MDP. After introducing MDPs, we started to describe some of the basic concepts of reinforcement learning. The policy tells the agent how to act in each state. The value function estimates the expected future return for each state or each state action pair under a certain policy. Bellman equations link the value of each state or each state action pair to the value of its possible successors. Finally, we introduced dynamic programming algorithms. These algorithms provide methods for solving the two tasks of prediction and control, as long as we have direct access to the environment dynamics. In the reinforcement learning problem, we will not assume we know the dynamics. After all, in the real world, we can't always expect to know the effect of each of our actions until we try them. Dynamic programming algorithms provide an essential foundation for the reinforcement learning algorithms we will cover in the rest of the specialization. Give yourself a pat on the back for getting through all this material. You now have all the background to understand the reinforcement learning setting. In the next course, we will discuss algorithms for estimating value functions and policies directly from experience. These sample-based learning algorithms do not require or even estimate the transition dynamics. Hope to see you there.